Okay, thanks for rolling up those who are here so far. We're just sitting and watching the attendee count climb a little bit, and we'll be starting in the next couple of minutes. Should be just enough time for me to fetch my water bottle, which I've forgotten. Yeah, sorry about that. So yep, attendees are still going up, which is good. What we learned from last week is it appears that YouTube has more folks joining it than the Zoom channel. It is, of course, entirely up to you. You get direct access to the chat in Zoom. Via YouTube, Christine, our moderator, has to shovel things across for me. Of course, entirely up to you. Okay, so maybe one more minute and then we will kick off. Right then, we shall kick off. Logistics are essentially the same as previous weeks. The sessions are being recorded. However, the comment about your camera is irrelevant because I don't think anybody is able to turn their camera on even if they wanted to. If you ask to unmute, obviously we will record the question that you put in, but you can equally put question in the chat if you prefer. We have the slides available for you to follow on as we work. Christine has popped them into the chat already. And if anybody's missed those or you want them posting again, then you can ask in the chat and she will send them out to you again. So the focus for this week is ftrace. Ftrace is the kernel's kind of inbuilt trace utility. It also has a heavy influence over how profiling is done, but we won't be talking about that this week. It's built directly to the kernel and it brings with it a really strong ability to see what's happening inside the kernel. So we're going to look at the variety of techniques that Linux uses and that ftrace uses to gather trace events, so the fundamental mechanisms. After we've looked at the fundamental mechanisms, we'll show you the tools that have been built on top of those mechanisms. And then there are a couple of little examples at the end. I think we've called them debug stories again. They're slightly different in character to the previous debug stories, which were deliberately very vague and abstract. And as we want to illustrate particular properties of the tools, our debug stories get a little bit more focused. But that's what we're going to be talking about today. Just to put it in everybody's minds up front, this is the sort of thing you get when you run a function trace. just so that everybody's got that idea of where we're going as we look at all the fundamental mechanisms. So this is a simple function trace. I say simple because it is only tracing function calls. So every function call in the kernel in this particular case is resulting in a line in the trace. So this is a file that we can read out from the kernel pseudofile systems, and it tells us things like what task it is, what PID it is, what CPU number we're running on, various flags that are interesting about the execution state, whether IRQ is on or off, whether there's reschedules, interrupt handlers, etc., etc. We get a timestamp, and we get the function that was called and where we were called from. So that's where we're going roughly. There are multiple tools that are built on top of the trace infrastructure. So this is just one example, but that's a picture for you to have in your mind as you look at some of the fundamental mechanisms. So this section is essentially a review of last week, but I think it's worth going over it again. So the fundamental mechanism that ftrace uses to allow us to put a trace probe into every single function within the kernel is compiling the kernel using the -pg option, profile generate. And the result of that is that every single function preamble will be compiled with a branch linked to a pseudo function called _mcount. However, during the build phase, I think it's actually the link phase, but during the build phases, the branch linked will be replaced with a no-op. It will be patched in so that the actual text sections that go into the Linux kernel and are loaded from the bootloader contain no-ops instead of branch links. So we've ended up reserving a slot in the binary code for these branch links, but they do not exist when the code is actually loaded by the bootloader. What then happens at a later point is we can request particular trace scenarios using debugfs. And as a result of selecting those specific trace scenarios, the kernel will walk over its own text section, replacing the no-ops with different branch links to a pseudo function called ftrace caller, which is what actually then hooks into all the trace machinery. And that allows us to instrument every function preamble to get a call into the trace infrastructure whenever that function is entered. Now, some of the things that we glossed over a little bit last week are the return handler. So it's all very well branching in on the ftrace caller during the function preamble, but eventually the function is going to return. And with that branch linked by default, you don't get the opportunity to add another trace event when the function exits. And that would be really quite helpful for building up command stack style traces. So we can actually cope with that. When we call ftrace caller, the first thing we do is call into the actual tracer and arrange for the trace record to be stored. After that, however, we can make some manipulations to the stack with this ftrace graph caller that intercept the return. Essentially, all we're doing is we're looking at where the return value has been stored on the stack, and we are modifying it so that instead of returning through the original program counter value that was pushed onto the stack, we go to a different place. We end up in this thing called the return to handler. And so essentially we go down the stack, we find the return address and replace it with our own return address. And then we store the original return address in a shadow stack. The reason we store it in a shadow stack is because, as I mentioned last week, Linux stacks are quite small, and we would not want to increase the stack utilization by intercepting those returns, because we might simply blow budgets if we've got a lot of small stack frames. If we add extra information on the stack to help us unwind, we would risk increasing the stack usage. So with the stack usage limited, we instead have the shadow stack so that we know that the instrumentation process cannot overflow the stack. And that's the whole of the interception process. When we call, we simply manipulate the stack so that we also get called. The trace logic gets re-entered when you return from this function. So now we've got the opportunity to intercept every function call and every function return. There was some other trace machinery that we're going to be introduced to at this place. So we're going to look at trace points, which are static pieces of code inserted into the kernel that can also log to the trace buffer. So in addition to all the trace events we saw at the beginning where we were seeing function calls, we can also trace specific events happening in the kernel. And what we see at the bottom of this screen is how they appear in the C source code of the kernel. We've basically got this tremendously funky macro called trace event, whose effect varies depending on when you're executing it, but by and large, you can think of it as defining a function. So trace event will result when it is expanded, it will be the function definition of a function called trace underscore shedawake idle without IPI. It will have a particular prototype, it will take some arguments, it will have some properties that it stores. So when the trace point fires, it will store some of its arguments into a trace field so they can be retrieved. And then finally, we have this rather neat thing called TP print decay, which when trace event is being expanded by a different piece of code, goes into a table describing the trace event and shows how to textualize it. In other words, it can take the binary trace field and produce a string from it. And that means that the kernel is independently able to create a string trace in that trace buffer we saw at the beginning by taking the trace event and running the textualized printk on it. That's the definition. The result of that relatively, I say simple definition, it is actually quite simple. Each of these macros, when you really drill down into them, is actually fairly simple. It only looks complicated because of the macro soup. The result of that macro, however, is that when you want to actually emit a trace point from your C code, it is as simple as you call a function and you'll jump straight into the trace logic and deliver your event into the trace infrastructure. So although the definition has a certain amount of macro soup in it, the usage is simple function call in the kernel. And that's particularly useful, obviously, if more than one part of the kernel emits the same trace event for various reasons, because you can call the function for wherever you need. So that's a static trace point. The final piece of infrastructure we're going to look at are kprobe events. So kprobe events are a mechanism to create dynamic trace points within the kernel. So we've looked at the static trace points, which are simply function calls into the tracing infrastructure. A kprobe is a way to dynamically add that almost anywhere in the kernel. You obviously can't add it to the kprobe infrastructure itself and to certain bits of trap handling logic, but the rest of the system you can put a kprobe almost, essentially anywhere in the kernel, and a kprobe internally is a breakpoint. So instead of the original instruction, the kernel will insert the breakpoint instruction and then allow us to carry on. So every time we hit that breakpoint instruction, we'll take a trap within the kernel. The first thing we'll do is go into the kprobe handler, which means call into the trace infrastructure and log that the event happened. Looking up some data similar to the static case with all those textualizing bits and pieces. That's created dynamically from the construction. And after we have put information in the log that we've executed that particular opcode, we then do a single step, which is done out of place, or out of line, they call it, execution out of line, XOL. It's executed out of line. Because this is an SMP system, you can't, what a normal debugger would do when you want a single step is write back the instruction, run a single opcode, and then replace the instruction with a breakpoint instruction again. That can't work when you're kprobing because another SMP core might be running the same text code simultaneously and you don't want to miss your probe events. So all kprobe systems have to execute and step out of line. So does it step out of line? And then it effectively exits back out of the trap again. So that's the low-level machinery. It is actually phenomenally simple. Breakpoints are a very traditional piece of code with trap handlings in it. Using the execute out of line technique is moderately new, but hardly groundbreaking. Function calls, they're not very sophisticated at all. Even things like the ftrace mechanism, when you look at the lowest level of machinery, it's actually quite simple mechanisms that are being used, but they do allow you to intercept execution anywhere in the kernel except in kprobe infrastructure and instrument it. So those are all the fundamental bits. We're now going to drill down a bit and look at how they emerge as tools we can use. So the really great thing about ftrace and kprobes and static events are that we can operate them almost entirely using standard Linux command line tools. ls, cat, echo, shell redirect is quite helpful. Simple kernel, Unix command line tools can be used to manipulate a tremendous amount of this trace system. You don't have to have special tools that run on the target to help you. And that's because the whole of the tracing infrastructure appears in debugfs in a directory called tracing. And this is the ls, the directory listing of that particular directory. One thing I'll wave at you right up front is this README file. This is a mini how-to. It's not a complete how-to. It doesn't train you in how to use ftrace, but it does remind you. I can't remember all the syntax to all the commands in ftrace, and I run this training quite frequently. But if you read the README, you've got a good shot at triggering enough of your memory to reconstruct most of how it works just from the README. You don't even have to open extra documentation. It's there in the kernel for you to look at. At this stage, I'll introduce a couple of files to you. So we've got some of the general controls. Current tracer is one of the most important ones. That's where we can write what tracing system we would like to run, like the function trace or some other tracing scenario. We have trace and trace pipe, which both contain the trace information. Reading from trace is non-destructive. Reading from a trace pipe consumes the data as we read it. And that's how we get that slide we had at the very beginning. We just cat trace pipe or cat trace, and that is the file that comes out. There's things like buffer size in KB. Obviously, any tracing system, you may have to tune the buffer sizes so that you don't circle too soon and things like that. So that's available to work with. It's a slightly funny order because it's better to look at the function tracing controls next to these green ones. So there's these filters that we can apply to ftrace. We can trace by PID. We can exclude things from being tracing. And likewise, when we're doing function graph tracing, which we'll get at in a little bit, the function graph tracing will also, we can filter those as we need. And then finally, I've mentioned the trace point events. So all static trace points are concealed in this directory called events. And we've got things like kprobe events to create kprobes if we need to. There's a question in the queue about the single stepping that I mentioned. Yes, execute out of line is a hybrid of true execution and simulation. So anything that's PC relative has to be simulated essentially. You can, on an ARM32 system which doesn't have hardware simulation, you actually have to single step, you actually have to simulate almost the entire instruction set. On an ARM32 system, because it has hardware support for single stepping, it's basically a lot of instructions you can execute and fix up, or you can execute and just simulate the execution of. But yes, because if you've got anything that's related to the current program counter address that your instruction consumes, or if it changes the program counter, if it's a branch, then we have to simulate that instruction, which we have code to do in the kernel. Okay, so simple function tracing we're going to look at. So we've seen how this is structured before. Perhaps we can go a tiny bit deeper and look at these columns now. So the execution state does tell us if the first dot says that IRQs are off. If it had letters in it, that would be a symbol that the IRQ is in some particular condition, where there's a reschedule pending, whether we're running it in a hard IRQ handler, maybe a soft IRQ, and the preemption depth if preemptions are disabled. So that's just a clue about our execution context. We have a timestamp, which is obviously important for any trace to help us understand the performance characteristics, and the function that has been called. This thing about strongly recommending enabling dynamic ftrace is advice to an architecture maintainer, to be honest. Dynamic ftrace exists. Everybody should have that turned on because I believe it gets wedged on by using one of the ARM platforms. Oh, thank you, Christine. Yes, I will make sure I read out the questions next time I answer one. Thank you. Okay, so function trace configuration. This is how to turn on a simple function trace. So in a lot of these cases, we've provided two ways to turn it on, one from the kernel command line and one from debugfs. So most of the time when you work with ftrace, you will be using the debugfs interface because it is most flexible. But if you are suffering problems during boot, if user space never comes up, you will never have the opportunity to interact with debugfs. And in that circumstance, we have this capacity to configure function trace from the kernel command line. So to do a simple function trace covering the whole system, you just say ftrace equals function and function tracing will be turned on. And then you can either use a debug tool to extract the ftrace buffer, as we were discussing last week, or you can turn on something like dump on oops, so that when a problem occurs, the whole ftrace buffer gets thrown out, so that you can see what was being executed when something bad happened. On the right-hand side, we've got a slightly more sophisticated way to set these things up. So first off, if you're running on a really simple user space, you might have to mount debugfs yourself manually. And then you can move into the tracing directory within debugfs. Once you're in that directory, we can simply echo function, it's the same word left and right, into the current tracer. You don't actually have to turn tracing on, but as you work with trace, you'll tend to get in the habit of turning tracing off to stop the fire hose every now and then. So it's just a worthy habit to get under your fingers to automatically turn the tracing on whenever you want it to be on, because otherwise you forget about it. But the default is it comes up with tracing turned on anyway. Once you want to see the trace, if the system hasn't crashed, we can simply cat trace. You can also rely on things like ftrace dump on oops if you would like to. And then finally, if we want to clear out data, we can disable tracing and clear the trace log. So we can write 0 to tracing on just to stop stuff being written to the buffer. And there are actually two ways to clear out the trace log. That's the least good. That is cat trace pipe to dev null, basically consumes the data and writes it. If you want a version that doesn't consume the data, you can actually just echo the empty string to trace, as shown there. There's not much of a muchness, but in theory, well, not in theory, in reality, cat trace pipe is going to take the entire of the trace contents into user space and then redirect it back into the kernel, which will ignore it because it's gone to dev null. The other form is a command to delete the contents. So it is more efficient. It doesn't involve transferring the trace buffer for user space to use the second form there. That's it for function trace. It is as simple as that. We will get to filtering, but for the basic setup of a function trace, that is all there is to it. A function call graph tracer is the other one we're going to bring attention to very early. This one is a tracer that traces both function calls and function exits. So this one's much more natural for the programmer because we can see the call graph, kind of the call stack growing and shrinking as we work through. And it actually presents like that as well. So the format of a function graph trace has lost the PID and TID that the PID and COM that you saw on the left-hand side of a previous trace. It just tells us the CPU number. It tells us the effective state of the system. Now we're looking at durations rather than strict timestamps, so we can see how long it took us to execute certain functions. Because we can do that, we can see when it loaded, and we can take away from the time it ended, the time it loaded, and we know how long it took to execute CPU load update, no hurt stop. And then finally, we're presented in a C-like annotation, meaning that if the function call has children, we see the curly brace to say we've got children, and then we can see all the children. So in this case, there are a couple of children. When you get to a leaf function, something that does not call any children, we get a semicolon to say there are no children of this node. The PID and COM are still presented to us, but it is only presented to us on context switch. And as we work through the context switches, we go back to our existing function call depth. So if you run this system wide, we've got very deep function call stacks, and this will start flying off the right-hand edge of the screen. But every time we get a context switch, we'll go away for a bit, we'll start a new stack. When we come back, the level of indent will be preserved. So as we context switch through these function call graph traces, it does remember the depth and show it to you correctly. Again, configuring a function graph trace is more or less the same story as configuring the function tracer. We've simply added underscore graph to the two different ways we can turn it on. However, whenever you set up a function graph trace, we are starting to drink from the fire hose, because the volume of trace coming out is very large. That can be okay. If we've got something to capture the data and put it somewhere, either to a high bandwidth disk or a network socket or something safe, that's not a problem. If we're trying to be a circular buffer, again, we can cope with high volume trace. The overheads aren't too bad, it's mostly binary. So compared to something like printk, which involves complex string formatting, the costs of instrumentation are low. But nevertheless, if you start doing a function graph across your entire kernel so that every function call is trapping into trace code twice, there is going to be a noticeable overhead. I will circle back. I mentioned that no-op insertion. What that means with the no-op insertion is that when you haven't got filters, when you haven't got tracing turned on, the overhead is very hard to measure. It is there, it will come out in iCache profiles, but it's very hard to measure. And more than that, certain of the filters we're about to discuss work at the no-op level. So for example, this line at the bottom, which is a kernel command line option to say ftrace equals function and ftrace filter on my drive _star. That means the only functions we're going to trace are functions that match that glob. Every other function in the kernel will have had its no-op restored, meaning that the trace performance now, the overhead of that line is very, very low because we're filtering out so much of the kernel. We obviously don't get very much information out in exchange. We only get to see that our driver's probed or when it's being called, everything else. But that is a useful thing for driver writers to know, and they might then turn on a few extra things that they know their driver calls so they can trace that as well. But that is a useful thing for driver writers to know that their driver was called when they thought it was. The line below that is a function graph trace, and it is not using the ftrace filter. It is using the ftrace graph filter. What the ftrace graph filters do is block a particular symbol name or glob symbol name and its children. And that means they can't work at the no-op level because they're contextual. So inside a spin lock, there is usually going to be, actually go for mutex. We've got some preemption disabling inside some of these functions. RCU certainly does. So inside RCU, there is a call to preempt disable. There are, however, lots of other calls to preempt disable. And since function ftrace graph no trace kills off the RCU functions and their children, it has to be done inside the trace machinery. So it's still relatively, it's much better than tracing it because we don't have to do as much work. But the graph-based tracers, because they're contextual, can't get rid of the no-ops. So you can actually run both these filters simultaneously as well. You can run an ftrace filter to say where the no-ops exist, and you can run a function graph filter to get rid of bits of trace we don't want. We will come to this in the live demo, the getting rid of trace you don't want. So we'll look at those concepts a little bit deeper in about half an hour's time. On the right hand side, I'm just doing the same type of thing, but using the debug fs interface. So we have this file called set ftrace filter, and we can echo sysread into it, for example. And then we can echo syswrite into it, and that will now match two functions. Notice the double chevron when we write to it a second time. I mentioned that we're using standard Unix command line tools to manipulate these files. That's because they implement something a bit like standard Unix file syntax. And if you were to use a single chevron to write to set ftrace filter, that would delete the contents of that file. Sorry, my phone's going crazy over here. I'm going to have to neuter it. So yes, if you use a single chevron to write to set ftrace filter, it would remove the existing contents and replace it. So it's very important if you're putting in a second thing into the ftrace filter that you do use a double chevron to append to it. And then if you want to clear it out, you can just echo a blank line to it. You can't remove them because it's a pseudo file system, but you can make the contents empty. I said it implements normal Linux semantics or normal POSIX file format semantics. That's not strictly true. It simply is a bit like it. And the thing that makes it different is wildcards. So just as we could use wildcards on the kernel command line, we can also write wildcards into the ftrace filter. So we've got a simple example here, SMCI star, redirect to set ftrace filter. When we read it back, we find out what it matched. So we don't read exactly what we wrote to it. We read back sorted, I believe, the list of symbols that have been matched by all the different globs and things that have been written to the file. There's some comments there about different globs and that certain glob shapes aren't there in older kernels. I think now that's becoming irrelevant, since even the most sort of slowest upgrading Android people are well past 4.9 by now. So yeah, you have got the full kind of glob syntax power. In addition to filtering, there are other things we can do with the same setFtrace filter file, and this is another aspect that's a little bit weird about it. setFtrace filter contains both the set of things that have no ops attached to them, which can be everything, and it also contains a collection of filters and triggers. So in setFtrace filter, we can perform certain commands. So the commands are actually slightly different in character. So mod is a bit special. Mod is actually more like a wildcard. Mod means I would like you to enable everything that is in this particular kernel module. So if you've got a modular driver, you can go in and say, turn on tracing for everything in my kernel module. It's quite a convenient shorthand to ftrace your driver. The other things are actually commands. It makes obvious sense for things like trace on, trace off. They say whenever you match this function, whenever you're tracing this function, I would like you to disable trace, for example, is quite a good one. If you're picking a failure point, have I got an example of this coming? Yeah, I have. So this is a really great example of what to do. You've got do bad area, which is one of the things that gets executed when you do something bad from user space. I presume it's a fault of some sort. Whenever you execute do bad area, we can set run the trace off command. And that will stop the trace, because probably we don't care what happens after the bad thing's happened. We just want to see the bad thing happen. We want to know what caused the bad thing to happen. We want to fix that, and we don't really care what happened after that. So stopping the trace when we see a particular function is just really comfortable for navigation. I've mentioned big traces are hard to navigate. If you stop them as soon as something happens, they become a whole lot easier to navigate. One thing that's going on there is you can see this do bad area .part.1. This is a consequence of something called partial inlining. So when we are working with ftrace, we aren't working with full C symbols. We're working with what the compiler put into the kernel. So inline functions you can't trace because they don't exist as far as the kernel is concerned if they were inlined. Similarly, if you've got partial inlining, what you've got is a situation where there's been some kind of fast path that the kernel has inlined into various call sites, and then you've got the long tails. And when you've got that kind of partial inlining, you get this part.1, which is the back part of do bad area. When it's decided something really bad has happened, we aren't taking an early exit path. So that's just to explain what the part is matching there. Before we move on from setFtrace filter, we'll quickly look back at some of the other commands. So trace on, trace off are quite intuitive. Snapshot is similar to trace off. It's particularly good if you're running an always on machine and you want to capture a collection of interesting traces. It will preserve the current buffer and swap to a new one. So that allows you to snapshot a problem while keeping running and keeping the debug code running to see if it happens again. We can reach in and enable or disable trace points. So we can turn on a specific wide set of trace points between a particular set of functions executing, for example. Stack trace is an obvious neat one. That just dumps a stack trace into the ftrace buffer. So you can look at a function and where it was called from. And then we've got some functions that can be quite useful if it's difficult to get the buffers out. We've got dump, which will simply provoke a dump of all trace buffers, or CPU dump. So where you've got code that you think might be executed, you could try and add traces on it to extract the trace simply by causing a particular function execution to cause the trace to dump. So that's a summary of the commands. We'll look at removing those in a minute. There are other types of things we can look at. So ftrace PID, set ftrace PID, is a way to restrict the set of processes that we are tracing. It's another good way to cope with trace volume if we believe the problem is caused by a particular system call. So it's no use if we think interrupts are causing the trouble because they don't have a PID. But if we think the problem might be related to a particular interrupt, sorry, a particular process, a particular system call, then we can use setftrace PID to do that. So we can just put in a list of process IDs. There is also an obvious way to trace the current thread, which is to echo $$ into setftrace PID. You'll notice in both cases we're using double chevrons. If you've got a means to reset setftrace PID to be empty, then being in the habit of using double chevrons is a good habit to be in, because it will automatically enrich things rather than clear out your previous trace. If you wanted to limit it just to a set of PIDs, you would use a single chevron. And we can use echo -1 to set it to a wildcard. A quick hack on the other side, or a quick a sneaky trick, if you like, is a way to trace a single process as it executes. And it's a shell script that wraps round, and you use it as shown at the bottom. You'd say something like trace me ls -lh, and you could look at all the kernel activity that results from running an ls. You'd be surprised how much it is. What we're doing is in our shell script, we are recording where we've mounted debugfs. So historically, debugfs didn't have a recommended place to mount it, and a lot of distros mounted it in /debug. So people who are a bit old like me quite often have these debugfs's in so that you can point to an old place. But the reality is that debugfs has had a canonical mounting point at sys kernel debug for the better part of a decade now, possibly more even than that. So the systems that don't mount it at sys kernel debug are long gone in reality. But some people do still parameterize this. So we're running our shell script. We echo $$, which is the current PID of the shell, into debugfs. We set up tracing, and then we do an exec, because when we do an exec, we replace the current process image and preserve the PID. So in other words, by turning tracing on at the last minute, then we will see the exec process. So we will see some remnants of the shell shutting down, but mostly we will be tracing the new ls process that forms instead of shell. And actually this last echo line will only be run if something, it will only be executed if something goes wrong, because the exec does not normally return. So that's a sneaky Unix trick to trace a single process. So from there, where are we jumping to now? Yes, we're now moving away from the filtering and function tracing and having a quick look at trace points. So what we're going to do, we're going to look at the trace points. We're then going to have a live demo that covers both function tracing and a little bit of trace events, and then we'll move on to some of the advanced topics. So the way I like to think of static trace points is that they are advice from the subsystem author of what is interesting inside their subsystem. So if you are trying to debug a scheduling problem, if you've got problems with task migration or real-time problems where there's a delay to executing a particular task or anything else, then the advice from the scheduler authors about what interesting things are happening inside the scheduler is a really, really useful stream of information. So we go to the shed directory, events shed, and we enable all the tracing events for the scheduler. I'll dig into that a little bit, but so yes, we've got this directory structure, and we can say go to all the scheduler events and turn them on. Then we can turn tracing on if it's a habit. And when we look at cat, now we've got that same familiar structure here, but the trace is no up. We haven't got any tracing happening in the ftrace world. We've exclusively got trace points. I will add, you can combine the two. You can have trace points and ftrace running simultaneously. So here we've now got, instead of the function being called, we've got the trace point. So we've got shed stat runtime, which is a way of sharing statistics about the scheduler with the trace point system, the v runtime and the runtimes. Shed switch, which is tracing the switch events, and so on. So you can then watch the kernel working, and we can attach higher value tools on the top of all the tracing infrastructure to visualize the task schedule from this. So how's that working in terms of the debugfs interface? So we've got the tracing directory we've been working in. We've got a couple of places to look at. We've got set event and set event PID, which are ways to write and set the list of trace points we're interested in. We don't use them very much when we're working with trace points interactively using command line tools. Set event is the sort of thing automatic tools like to use. because it's compact and it's easy for machines to interact with. But as a human, I find working with the directory structure for events much more comfortable. So you have got this set event directory that can allow you to enable and disable different trace points and filter on PIDs and other things. But I actually much prefer using the events directory just because it is more intuitive and more comfortable. So if we move into the events directory, we have a whole bunch of subdirectories. So we've got the shed directory, which we were working in a second ago. And we've also got a file actually called enable and a whole bunch of other directories. So these are all the things that on, I don't know whose system this was, I can't remember, but on somebody's laptop, I would imagine, these were all the things that you could gather trace points from, including this enable. So if you go to enable and write a 1 to it, then every trace point in the events directory and its children will be turned on. In other words, by writing to events enable, we can turn on every single trace point in the system. We can also go inside the shed directory and look a bit closer. So inside the shed directory, we've got another enable, which is the one we were writing to a minute ago to turn on all the scheduler events. So the enable in events shed will enable all the events in events shed, which are all these events. So it's only 2 levels. There's the top level name, and then there's the name of each trace point. So these are the list of all the trace points that exist in the scheduler, all the interesting things that the authors wanted to share with us. So we can look at those with ls. We can go into directories to learn more about them, where again we have an enable. So we have 3 levels of enable. We can enable everything, we can enable everything in a category, and we can enable specific individual trace points if we so wish. There are also other files there, but I will mention them now because I can't remember when these come up next. So we have filter, which allows us to attach filtering to trace points. So we can match PIDs, we can match arguments. So particular trace points, classically, for example, if you're using the I2C trace points, you can filter on the address. So you can only sniff the I2C traffic for a particular peripheral that you're trying to debug. Simple example. We've got format, which tells both us as humans and visualization systems how to present the trace point to people. And we've got an ID, which is mostly used, we mostly read that out, and then that is used in things like the perf events API. We won't meet that till next week. And then trigger, which is a command, it's basically commands we can attach to trace points. So just as we added triggers using setftrace filter for trace on, trace off, stack trace, we can also add stack trace triggers to trace points as well. So I think I'm now going to have to slowly work out which bits I've been repeating and not repeating. Configuration from the kernel command line. You can configure trace points from the kernel command line, just as you can with ftrace. In fact, there's a couple of bonuses here. So first off, you can use trace event to list the events we would like to enable. We also have a command line option called tp-print-k, and that simply arranges for trace points to be textualized onto the console as well as textualized into the ftrace buffer. In other words, we don't have to mess around with dump on oops or anything else. If you had trace event and some trace points and tp-print-k on your kernel command line, then you would be seeing them on the serial port or in the dmessage buffer as the system boots. So if you want to know, for example, what thread is running just before something bad happens, we can actually study that with trace event shed switch, point it to tp-print-k, and that will print as we go. Every context switch will get printed as it works. On the other side, we do have set event, as I mentioned. So that gives us things like we can echo shed rake up into it, just as we had in trace event. We can echo wildcards, and I believe the same wildcards that work here would work in trace event as well. So we can match particular wildcards. But like I say, I find when I'm working interactively, it's just more comfortable to look in the events directory because you can ls and you can check the format and you can find out what something does. And you can even use find to find trace points. So this is the mechanism I prefer, and those are the 3 levels that we talked about a couple of moments ago. So diving deeper into trace points, this is code very similar to the macro soup I showed you before for a much more complicated situation. So there's a couple of things that make it more complicated. Firstly, we're now declaring an event class. rather than a specific event. In other words, if we have a number of trace points that all take the same arguments, we can summarize the arguments once and then have multiple defined event calls to create multiple functions that all trace different events. They've got different names, but they can share arguments. So a lot of the scheduler stuff will share a few arguments, target CPU priorities, things like that. So instead of a single structure entry, we've now got, sorry, going back, the original one we looked at before had a single integer argument called CPU. This one has a single argument, but it's a structure. So it's a single structure that becomes multiple fields when it gets written out to the trace buffer. So we extract from the task struct the various bits of information we think are going to be interesting. So we're sucking those out of the task structure. That I think is summary information. This is how we actually grab it and get it out. So this is the code that actually extracts and writes to the trace block how we actually get it, and we've got the mechanism to print count. These macros are quite exciting. I mean, I started following a source nav. It is quite a challenge finding out how they work. It's kind of interesting. You don't need to know how they work to use them, but I was kind of curious. So it is quite an education going to read these macros, but I'm not going to go into that in too much detail at this point. However, that trace format, this TP struct entry here, comes out again as part of the format file inside a trace point. So we get to see the ID, repeated again in case we want to use it. We also get the format, and all the formats contain a certain amount of common information. So things like the event flags, type, preempt count, the PID, those are all present in all trace points. They're common. However, the specific self-defined fields, you should recognize these as the same set of information that was presented before, but all carefully set up with all the binary information to help a tool extract it, store it, describe what it is, and manage the data that's been coming out of the kernel. And then finally, for the text-based trace tools, we've got the textualization description. How far have we got? That's it. Right, so two more things to talk about before we go to the demo. So trace event filters. There are two types of filters that we can apply to trace events. As I mentioned, we've got the set event PID, which is in the top level, appear to set event, and is exactly analogous to set ftrace PID. So you know how to use it. You can echo a collection of PIDs to it, or you can use $, or anything else, and that allows you to filter by PID. And if you are doing PID filtering, this is marginally more efficient, but if you're worrying about the efficiency of your trace system, you might have more significant problems. The filters that you have in the local directory for each trace point are much more powerful. They allow us to write these little expressions to trace things. So they're C-ish, they use C-like operators, they use things like and or brackets to combine the predicates if you wish. So you can, for example, look for tracing PID 0. I think tracing PID 0 is a very bad idea because it's reserved. Tracing 1 might be interesting. I'm not sure tracing PID 0 has any value whatsoever. You could look for things that have a priority more than 90. So real-time priority, I think, is what that would be dragging if you're attaching it to scheduler events. There is an additional thing, which is this tilde, which is a globbed string match. So in addition to the integer operators, we also have this wildcarded string match if we wish. So you can look for example, you can filter only testing away from a particular test task when you are gathering your test filter. So that's what we can do with the trace event filters. They allow us to reduce the information and focus in on specific events of interest, or we can just gather them all and filter them after the fact like we would with other tools. And again, we have triggers which can be useful. So trace on, trace off, similar to what we saw with set ftrace filter. We've got snapshot just as before. We can reach in and cause one event to chain and cascade other events. We have stack trace, which is almost certainly the one you use most often. And we have the histogram, which I am going to get back to because it's one of the things that takes a little bit of time to digest. So a quick example of a trigger. Bear in mind, it also has access to the predicate language. So we can say things like trace off if the main process has exited, is what that basically says. So we've attached it to the shed process exit trigger. So if a process called main exits, then we will stop tracing. May or may not be useful, but we have those kind of capabilities. So, oh, I meant to reset this. We have a emulated system at this point. So I wanted to show you a rough idea of how you might sit down on a very Spartan system and do some debug. So this is a very simple build root file system. It has minimal tools. It's actually a BusyBox based system. So I'm not even having full GNU tools as my Unix tools. I've got a simple BusyBox system. And as it happens, this particular system doesn't mount debugfs by default. So I'm going to mount it at the canonical location that we've talked about before, which is great. And from there, I can enter syskernel debug tracing directory, and that ls should be fairly familiar to you because it's the one I showed you on the slides a little while back. And that is the tracing mini how-to. So like I said, this is a collection of memory joggers. It is not in-depth description of how each of these features work. So you can look up echo 0 tracing on, echo 0 tracing on. You can look at how to study the current tracer. You can see about the buffer size or total buffer size and other things. There's one particular one I wanted to bring to people's attention, which is set ftrace filter. Because set ftrace filter has the two things globbed together in it. You've got the set of things to which the ftrace caller or no ops have been selected, and you've got the triggers. That makes removing triggers quite difficult. So it actually gives you some reminders about the correct syntax to disable a trigger, because it's very easy to accidentally set a trigger on and then forget how to remove it again. So if that ever comes up, you can look in the README and it will remind you how to do it. And it contains reminders for most of the rest of what we're going to be talking about as well. So that's not wrapped very well, so I'm going to clear at that point. So in our directory, we do have that set of available traces. So far we've only looked at a few of these traces. We've looked at no-op, we've looked at function, we've looked at function graph. We did briefly talk about some of these in the debug session last week. But these are the traces we have available to us. And as we looked at, the simplest way to start tracing is to put a function into the current tracer. You saw a tiny delay there before it gave me my shell prompt back. That was the time it spent to, in a simulator, walk through the entire text segment, replacing the no-ops with branch links. And I have to say to you, the performance of that has gone up quite a lot since I was last running these kind of demos. It might be because I'm using a faster machine in my garage, but I think it's actually because this QEMU has got a little bit better at following that kind of stuff. So we've replaced all the no-ops, and if we look at trace right now, it is throwing out gallons of trace at us, even on this idle system. So this is a simulated system with no real connections to anything very much. It's idle and it's still throwing out a tremendous amount of stuff. And in actual fact, what it's doing right now is showing me the trace, and we're just accumulating trace after trace after trace after trace as we run. So we will see a vast amount of stuff happening as we make various calls. So this is a kind of drinking from the fire hose case, and let's try and reduce things a little bit. So I'm going to echo block star to set ftrace filter, and that will, you saw again the small delay, because what that's done is it's gone to every function in the system that doesn't start with a block and put the no-op back. So we've got almost full performance again now, because there's only a very small set of functions that are running with a filter on it. So we can cat the ftrace filter, and you can see that I've picked up the blocking notifier stuff and the block. And this is an obvious warning about using wildcards, is that they can match things you didn't mean them to. If you wanted to match blocking, write blocking. If you wanted to match block, whack in the underscore. However, I didn't actually mind matching the overmatch at this point. So if I echo to trace to clear it out, then I can cat trace and it is empty. How bizarre. However, if I run it again, so what's actually happening here is that the first time I ran it, there was nothing in the trace buffer. The act of running cat trace on the trace file causes the blocking notifier call chain to run. So basically, every time I run trace, I look at the cat the trace buffer from now onwards, there'll be a single extra line containing the blocking notifier call chain that was run as the cat process exited. You can tell that when I construct demos, they try to self-stimulate. So it's very convenient when you're doing trace demos to run programs that self-stimulate, because then the audience can understand what we're actually looking at. Now, on some systems, you also see the block activity when you're in a sync, but this one is running from a RAM disk. So if I'd been running from a real file system, when I'd done the sync there, you would also see block activity in the trace buffer. But because this particular simplified system is running from a RAM disk, it's really pretty much impossible to provoke block activity. So let's add a few extra functions. So I'm going to go and hit a selection of wildcard that is pretty wide. So set ftrace filter. You'll notice that I have remembered to use my double chevrons, which means when I run this, the set of functions we should be tracing are all the functions that contain the word alloc and all the functions that start with the symbol block. And we can see that if we look at set ftrace filter, we can see what it's mapped. We can see there's a lot of allocs. All the blocks have flown off the top of the screen, but we can use a grep if we want to. Like I say, these are Unix-like files, and we can run Unix-like tools over them. So I can do a grep. I have to admit, it was a complete coincidence that fitted exactly on the screen. That wasn't something that I'd pre-planned. And now when I look at trace files, we will see a fairly significant flow of activity going on. It's not unbelievable amounts. It's a quiet system after all. But when we ran the cat, we did do a whole bunch of memory allocations and other things. Now you'll notice I haven't got my prompt back. And that is because, I don't know if you caught it when I ran it, but I ran from cat trace pipe instead. So cat trace pipe is the destructive version of trace. So there shouldn't be very much trace information in the trace pipe right now. But if I run cat, there will be, as we allocate all the pages to support the cat process. So there's not very much in there at the moment because I cleared it out when I ran cat. The other property that trace pipe has is that it stays open. So if you've got low volume trace, as we do here, it's quite common to throw open a terminal, cat trace pipe, then go and influence other things to stimulate it and just watch it come through as dynamically as you need. So this is like what using tail minus F, or following the end of a file. Okay, so at this point, I'm going to introduce a trick. It's a demo trick, to be honest with you. Have I still got it in the trace buffer? Yeah. So when you are running a live demo and you are working to change all the different files in your system, it's quite easy to get lost. You think, oh, I'll just show them this. I'll add some value. It's not in my script here, but I'll just show them an extra thing. And then you get lost and you forget where ftrace was. So this cleanup script is quite useful. It's the one I use to clean up in demos. I do occasionally use it in real life as well. And it's basically built around this slightly sneaky little tracing function, which uses T to write to a file and also to keep it dusted out. Now, that's not very helpful in this form, but when we swap around the comments so that this printf and this T are uncommented and the other T is commented out, it basically tells us what we're doing. So it's currently set to run silently, but if you flick around those comments in the top section, it will tell you what commands it's running. And if you're using that macro to set up your own tracing scenarios, that's just quite convenient. It's what I use when it's basically a trick that I like to use when I am writing shell scripts to configure the trace for me and unconfigure them. But ultimately, it's very, very simple. We are setting the tracing off. We are setting the current tracer to no op. We're then disabling all the events and removing all the dynamic events. We haven't seen about those yet, but they will come up later. They won't be demoed as it happens on this occasion. We clear out all the filters, we clear out all the no traces, we reset the function graphing, and then finally we empty the trace buffer and put the tracer back on. So it basically puts us into something like the factory settings. It's not perfect, because if you've got any triggers set up in your set ftrace filter, they will not be cleared, because set ftrace filter is this bizarre file, and we'll come to that in a moment. So I've got my cleanup thing, and if I put it in the path and make it executable, then I can clean. Oh, interesting. Did I spell that wrong? Oh, I haven't got it. Interesting. Okay, I'll have to cheat. I told you it was a stripped back system. Oh, it's my fault. That's what I've done. You can see what I did there, can't you? Anybody who's old school have recognised that I forgot to put the path, the rest of the path in place. So that will work rather better now. I had to have something in the demo to throw me off my game a bit. Sys kernel debug tracing. So slightly longer than I intended to spend resetting the system, but we've now got a clean system to run the next example. So we'll look at function graph tracing. Now, function graph tracing really is where we can seriously drink from the fire hose. So when I run cat trace now with the function graph tracer running, I've still got the filter in place. You saw that take a very long time, and that's because the function graph tracer is running simultaneously to me turning on all the no-ops, which is creating quite a lot of function graph activity. So now when I cat the tracer, we're seeing an immense amount of data. This is a 110 column terminal, and you should see every so often we are flying off to the right hand side as we dive up and down the stacks. It's quite hard to see what's going on from this. I don't know if it will still be in the trace buffer, but usually there are little markers in the left-hand column telling us how many events we've lost, because we are simply gathering so many events so quickly, we cannot possibly even push them out to our serial port quick enough. So this is full drinking from the fire hose time. We have got too much data. So we want to think about how to reduce the amount of trace we've got. So one trick is to get rid of all the logs by putting them in set ftrace no trace. Now set ftrace no trace is essentially the opposite of set ftrace filter. It contains a set of things you don't want to profile, forcibly putting the no ops back. So we can do that echo star lock, and that should give me an error. This is a deliberate error that I have put in for you because I have not put quotes around the lock. Now generally, when you're working with these kind of globs, you can get away without the quotes. But the reason this doesn't work is because there is a file in the current directory that matches starlock star, a file called trace clock. And that means that instead of writing starlock star into set ftrace no trace, we are writing trace clock, which is not a symbol in the kernel, and it gives you an error. So just to explain what's going on there, normally, if you have a pattern that isn't matched, then the shell won't expand the glob and the stars end up being passed to the subprocessor or to the redirect, wherever else it's going. But if the file does exist, it gets glob substituted and we lose it. So in general, we try to get in the habit of using quotes around the wildcards to prevent the shell from interpreting them for us. So now we've got rid of the lock. Just to show you that it does work sometimes, I know that there's not a file called __RCU in the current directory, double redirect. So I can use that to remove the RCU functions from set ftrace no trace. And then I think there's one other set that I like to get rid of, which is preempt. Yeah. Now what you might notice at this point is that these echoes are getting very slightly faster as they run, although that one's punished me by not being. So we are getting less trace information as we've worked here. So it shouldn't be flying quite as far to the right hand side now because we've got rid of some of the things we didn't want to see. It's still more than we can cope with, much more than we can cope with. So the other thing we can look at is set graph no trace. So the previous one we've been looking at is set ftrace no trace, which says preempt functions, we don't care, never even enter the trace machinery. But we can also echo something like git candle IRQ, which I've picked simply because it's there, and write that into set graph no trace. That says don't trace any children of GIC handle IRQ. Just ignore the children. They will still call into trace machinery because they've still got their calls into ftrace caller, but the ftrace machinery will discard them almost immediately. And if this were to occur, if I ran this now, then GIC handle IRQ would have a semicolon after it, because as far as the trace logic is concerned, there are no children because we didn't trace them. So this is a really effective way to prune big chunks of call tree that we don't care about. So when you're working with a graph profiler, you usually do a couple of traces, just as we've done here. We look for things we don't care about and we get rid of them. Now, the trace volume will still be very high, to be perfectly honest with you. So it will be very hard for you to see, if I count this out, that GIC handle IRQ is not being shown. But you can hopefully trust me on that one, that's not happening when we do this. So I'm a bit worried about the cleanup because it didn't seem to clean up all the things that I was expecting. It's not. So I rewrote that just before I'll do it by hand. The cleanup function, I rewrote midday, and then I've got distraction. I haven't been back to tidy it up. So I do use that tracing macro frequently, but I appear to have transcribed it wrong. So it hasn't worked correctly, and it doesn't actually act to turn off the trace or cleanup for me. So apologies for that. It's me changing the script and then getting distracted. So I will have to make sure I do not forget anything else for the rest of the demo. But there's not that much to go now. So oh, not least because I've gone to the wrong part of my script. So I'm going to put the function graph tracer back on, but we've got rid of all the filtering. So we turn the function graph tracer back on. I just want to show you the subshell trick. And I'm not going to run it as a full script. I'm going to start a subshell. I'm going to change the prompt so that you can recognize that it's a subshell. So whenever we see this subshell prompt, we know we're running this subshell that we've created. And I'm going to write echo $$ into set ftrace PID. So now the current shell will have been written into ftrace. So the current process ID of the subshell has been filtered, and that's the only thing we're going to see. I'm then going to wipe out the trace to make sure that all the previous function tracing has gone. It's no longer relevant to us. And then I'm going to exec dd equals /dev urandom. And I'm going to grab a few files of pseudorandom data from the entry pools. I've got an exec, so as soon as I have run it, the exec finishes, and I go back to my parent shell, which means now the process that we were tracing doesn't exist. And if I ran trace, we can see what we were attached to. Did I forget to clear out? That's actually rather less than I expected. I've probably forgotten to clear out one of the filters. Demoitis. Let's try 0. I have to say I don't understand why that isn't working. That usually does. That's a bit of a worry. I might have to reset if I can't remember how to clear that. That would never normally be happening. Oh, empty string. That means I have to update my slides because there's an error in them. I beg your pardon. Right, let's get back to the next part. There we go. So cat trace should be showing us lots of stuff. Yeah, that's fine. So I'm going to write not back into the current tracer. I'm going to clear out the trace. And quick look at some of the other bits and bobs that we could be doing. So we talked about do bad area. I'm going to use a wildcard on my do bad area and use a trace off command. So trace off command and write it into set ftrace filter, and then look back at the contents. So this is the curious property of this file. We've got all functions are enabled, and we've got a trigger trace off on do bad area on the semi-inlined, the partially inlined system. So we can add to the ftrace filter, and we can use colon to set the commands, and they're effectively different. If I were to put echo block star into set ftrace filter and then cat it back, sorry, ftrace filter, you can see that you've got the functions that are enabled, and you've got a set of commands at the bottom. And if I echo and try and clear out set ftrace filter and cat it back, it has only cleared out the function labels. It hasn't cleared out the triggers. And this is what I mean about the incomplete cleanups that can happen with the cleanup script, even if it was working correctly. And somebody said the reason it worked is because I forgot to call it, which would be comfortable. It'd be reassuring if that was true. I hope it is. So cat set ftrace filter will only clear out the things that we've selected. We have to, if we want to get rid of the triggers, we have to explicitly say we'd like to get rid of the trace off triggers. This is what I mean about reading the README file to remind yourself the syntax of that, because it is quite difficult to remember the syntax for triggers. And now when we read set ftrace filter back, it's empty, it's clear, which is great. Now, there's only a tiny bit of demo left, which is good because we need to have a break shortly. So we're looking at trace points now. So the tracing system is all defanged and disabled, but we can go into the tracing system and start gathering trace points. And now when we look at trace, we'll start to see vast numbers of trace events dumping out into my trace. And almost all of them are RCU dyne tick and a couple of interrupts. Turning on all the trace points is still a little bit like drinking from the vase. You get too much information. So much more commonly, we can go into events and we can decide what it is we want to work with. So, you know, you can do things like, I can go to I2C and enable all the I2C events or disable them. You can see with the slashes after them, those are the actual I2C trace points. Now this system doesn't emulate anything on the I2C bus, so they're not very interesting for us to look at, but they are there because they are part of the I2C subsystem. One of the things we'll look at is the IRQ enable and disable. So we can go into IRQ enable and disable, which we saw in the trace a little while back. And we find it's rather odd because IRQ enable and disable isn't actually in the IRQ directory. However, we've mentioned the joy of being able to use standard Linux tools while we work in this space. We can run a find across the I should have an extra star on there, shouldn't I? We can run a wildcard search across the directory structure, and we get to find out that IRQ enable and disable, which are one of the things that is contaminating our trace, are in the preempt directory instead. So if we want to get rid of those, we can echo 0 to preempt IRQ enable, and that will get rid of all the preempt IRQ stuff. We can get rid of all the RCU stuff. We can clear out the trace so we don't see the previous stuff. And then when we look at the trace now, it will still be noisy, but we've got less. We've got more interesting things happening. We're not being so deluged with RCU timeouts that we can't see anything else. And usually you get rid of most of the other stuff, soft IRQ, all the stuff that happens all the time. And then you'd just be left with some of the most interesting things in the system that could be going on. It's a great thing to do on your laptop if you've got a GNU Linux laptop, is to, I really like watching I2C because the trackpad is I2C, the keyboard is I2C, the touchscreen is I2C. So you can get a really good sense of how you can use trace points on a system that's fairly understandable, because most people have a good view and understanding of how the I2C bus works. And that's almost it, except for looking at the formats. So I think we will look at the I2C stuff because it's fairly intuitive if people understand what I2C read does. So when I show you the format for it, it should be relatively comfortable for you to recognize this format structure. So this is one of those trace points. I think there's about 2,000 odd trace points on even a fairly quiet machine these days. So we've got the 4 common fields. We've got the adapter number. We've got the message number. Then we've got the address, which is just the I2C address. So we can run filters on the I2C address and only watch particular I2C bus transactions. We can look for oversized things. We can trace every I2C read in the system. We can put one interesting thing to do is to put back traces on I2C read so that we know where it's been called from and we can find out all the driver stacks that are called. That's not so interesting on a laptop because they all turn out to be called from the HID driver, but it can be interesting on a more complex embedded system. And that gets us towards the end of the demo. So I apologize for the strange cleanup in the middle, but I hope all the concepts have come through well for everybody. At this point, we are going to take a very quick break, and I do mean quick. I think we will come back at 20 past the hour to continue with the last bits and pieces. So that's just 4 minutes to try and absorb and work out what you're doing. If anybody has any questions, you're very, very welcome to place them in the chat. I am very happy to take questions in this gap. I don't get to go anywhere right now. I just get to drink my water and chat to people who care to chat to me. But if anybody does need that break to rush out the room, you've got 3 minutes left. So I hope the demo was clear for everybody, despite the cleanup. Like I say, if there's anything that you think I missed while I was walking through that, it should have given you a good sense of how things that we've looked at so far fit together. It's quite curious. I think we're likely to share the videos from the US sessions because I don't get as many questions for whatever reason. In the European sessions, I get so many pings from the group chat that I lose the thread of my thoughts a little bit too often, which is fine because it means I can answer people's questions, but it does mean the videos from these sessions tend to be better. So yeah, just a minute left and then we will get back to the material. Okay. So we're going to launch back in with one of the most powerful and sophisticated and hard to remember features in the entire F-Trace. It's why we've picked it up after the break, to hope that it tries to settle into people's minds, because it's quite an exotic feature, this one. But it's also quite powerful. So trace event histograms. Hist was one of the commands that you can attach both to ftrace and to trace points. And they allow us to gather up hit count information about stack traces, which is a really big deal. So there is almost no chance you'll remember the syntax for this. When I move my mouse, it comes up behind the pop-up. The syntax to do this, we say hist, and then we have a bunch of arguments going into it. So this particular case, we've put a request onto kmalloc, and the trigger we've put in is hist, and we want the histogram to have two keys, the stack trace and the number of bytes requested. And what that will do on the right hand side, when you cat back the histogram for that trace point, is it will show us the stack trace, the number of times that stack trace has been called with a specific number of bytes requested. So you can basically use it to look both for who most frequently allocates data and who most frequently so which places we have most frequently allocated what amounts of memory from. It's a really strong view of who is the person who is working your allocator most hard and by how much they're asking it for. If you remove the values equals bytes rec, then you would just get the hit counts of who calls malloc most frequently. Now that's already quite cool. But when you attach it to something like ftrace and get who has called this particular function the kernel most frequently, it's a very simple poor man's profiler to allow you to find out who is hammering away at different library functions. So I hope it kind of makes sense what's going on. So normally, in addition to this stack trace, there'll be lots and lots of other stack traces further off the bottom of the slide, showing different stacks that have called into kmalloc, how often they called it, and how many bytes they requested. We've got a question in the chat about exfiltrating data. I think we'll come back to that because yes, there are other ways to get data out, and they come up as we look at some of the later tools. This is something for you to keep hold of. There's no need to understand it now. This is just a summary of some of the ftrace related kernel command line arguments. Because we've been focusing, particularly in the demo, on the using of simple tools to manipulate the tracing infrastructure, these are the equivalents for most of what we've talked about that can go on the kernel command line and allow you to set up the same trace scenarios at boot, so that if you've got an incomplete boot, you can still have an ftrace going on. Trace print k is quite an interesting thing. Trace print k is a function call inside the kernel that can inject data directly into the trace log. So you've got a simple call here. We've got a trace print k, read through into bar, and it comes out on the tracer pretty much a bit like a trace point, except that it has no metadata. You can't hook it, you can't track it, you can't grab hold of it. It can, however, be very useful for helping you navigate a trace buffer. If you have the time and inclination, it's better to create a trace point. But if you're doing a quick hack in a piece of code that you're recompiling, you can whack in a trace print k and it can help you navigate the trace by saying what events have lined up inside your driver to what function calls are happening around it. It is very likely that if you grepped across the kernel, you won't find any calls to trace print k. They are very much intended for quick hacking, basically. It's there to help you understand logs, but most of the times we make any kind of commitment to a log buffer, we use a trace point when we're working inside the kernel. Finally, we have trace markers, which are essentially the same as TP print k, same as trace print k, but from user space. You can write to the trace marker and it will pop out in user space. So you can then align user space events to kernel activities. This is fairly infrequently used, but it does come up a fair bit in Android. So I think the systrace tool is able to align certain interesting user space events so that you can examine what's happening in the kernel as things go. So we talked right back at the beginning, hour and a half ago now, about dynamic probing. So what a dynamic probe is a trace point that we can attach to a breakpoint. But it's a breakpoint that automatically resumes with a single snapping. So we have this special file called kprobe events that we can write this special syntax to, saying p:, name of the probe, and the function we want to attach it to. That's pretty much the simplest form of syntax we can throw into this thing. It is, like everything else, I believe, summarized in the README file. So if we do that, open into kprobe events, we can then go into the kprobes directory within events and look at my probe. And my probe just looks like any other trace point. It has an enable, it has a filter, it has a format, an ID, and a trigger. We can put histograms on it. We can pick any function in the kernel and get that same histogram trace that I mentioned via trace pointing by putting a probe onto any function we wish. We can look at the format. So in this case, the format is fairly bald. We've got the 4 standard fields, and we've got the IP address that we actually probed at. That's it. That's the default. So we didn't ask for any extra records to be stored. So we didn't get any. We just got the probe IP. And we got the, so I need to get the mouse still to see the stuff at the bottom. We've got the printk format, which just shows you the IP address. And then we've got that -:myprobe syntax that we can use to specifically remove a probe from myprobe event, kprobe events. You can have multiple probes in kprobe events. So if you want to targetedly remove a single one, you can use the double chevron append. If you want to wipe out all the kprobe events and start again, you can echo the empty string and it will go away. So maybe we don't want to trace the function entry point. Maybe we want to trace something else. So this line at the top is a instrumented version of the C. So we've got the C and assembler side by side. I think this comes out from objdump. I'm actually a little fuzzy on my recollection of where it's come from. So I'm also being dazzled by the sun coming through my window. So it's drawing together the disassembler and the original C source code and telling us where it will be loaded. So like I say, I forget the tool that's been used to drag this out, but it does mean that we can put a probe on a opcode by address. By whatever means we've gathered the address of it, we can put a kprobe on the opcode and we can gather the trace information. And now when my probe runs, it doesn't just say update min v runtime, it shows us the offset. Incidentally, if you wonder what's happening there, %lx is the textualization of the thing that happens to mean symbolize, convert it to symbol form. So rather than seeing the raw opcode, we do see the thing in the offset. So that's kind of interesting, but let's do better than that. Let's look at return probes. Now, return probes are interesting because we can add arguments to them quite easily. So we use R instead of P. So this is now going to probe the return of the function. And we've got this $retval, which is a substitution to say, show us the return value. And we put that into kprobe events, and we run kprobe events, we enable it, we look at the trace, and now in addition to the IP address, we also get the first value that we listed in the top. So it's called arg1 because we didn't give it a name. So $retval has been automatically given the name arg1, which is marginally confusing. And we've got back 3, which is the normal case. For most programs, they have stud in, stud out, std file descriptors 0, 1, and 2. And when they open a new file, it goes and gets the next available file descriptor, which is 3. Typically, most programs then close that file descriptor, open a new one, and they get back the file descriptor 3, which is the first available file descriptor. So this is a very, very common pattern. If you start probing deuces open, seeing 3 returned is by far and away the most common value that's ever going to come back from deuces open. So what we're seeing back kind of makes sense. We're getting sensible return values as we watch this probe trigger across a variety of CPUs. Let's do better because we don't think that tracing just the return value is enough. Let's look more deeply at the arguments. Now, we looked at the ABI last week. we saw that when you are entering a function, x0 contains the first argument, x1 contains the second argument, and so on. So as we probe, we can put in arguments. Just like the retval substitution, we can follow particular registers. So when we enter update minv runtime, we would like to create a argument. This is no longer an anonymous argument. The CFS equals means don't anonymize, don't call it arg1, call it something else. So this is called CFS. And we would like CFS to be a 64-bit hex number read from the 0th register. So now what we're doing when we run this is probing a function and showing the first argument. And this is where we're starting to change what we can do with kprobes, because this is no longer something you could do with ftrace. Ftrace doesn't allow you to sniff arguments. Whereas when we stick a probe on something, we can grab arguments. Now, what I will mention is if you're on a mainline kernel, you don't have to remember the ABI. You can use $arg1 and get the first argument. Just like you have $retval, you can have $arg1. That was upstreamed relatively recently. So if you are, I can't remember the version number, but certainly if you're on a 4 series kernel, you won't have that. It's about 18 months ago, isn't it? So roughly 18 months ago, this kind of landed mainline. So as you move forwards, if you're a very up-to-date kernel, you can start using $arg1 instead. But for now, we have left it in x0 form for x86 users. ARM people who are using 32-bit ARMs, you still have that same theory. It's just you'd be using %r0 rather than x0. Can we get more out? Well, yes, we have tremendous capacity to CFAR, providing we can express in a machinish approach what we want to suck out. So this is an instrumented trace that tells us that we can see where it dereferences CFS RQ and gets them in vruntime, and it stores vruntime into the second register. I will add that obviously these interleaved instruction and text views are very good for learning about assembler and what is actually being meant. But yes, this is dereferencing x19 offset 40, which will be the min vruntime offset, and it's storing an x2. So we can attach a probe. We don't have to use the opcode. We can use the offset. So where we used just the IP address previously, we can just use the symbol and the offset, which is much more comfortable in many circumstances. So we're saying at offset 1C, we would like to probe it and gather the value of x2 every time the trace point runs. Terrific. Oh, and it does remind me, yes, it is using objdump to get this view. I thought it did. So we can really go quite deep with this stuff. We can do even more. We can follow pointers. At this point, the syntax does start to get a bit baroque. There's no two ways about it. The syntax does start to get a bit baroque. And what we've got is all the P stuff, the P, the probe, the function name we're attaching to is all familiar. Task name is just giving that arg1 a name, which is great. The probe, somebody's asked if the probe runs after the instruction targeted or not. That's an interesting question because that is definitely picking up x2 before we've written to it. I think it might actually. I honestly can't remember. I think it probably does, but I will have to double check that. I certainly won't risk an authoritative answer now. It is in the flow actually on the slides. What is slide 7? There is a flow, and there was a second box with a second bite of the cherry, but whether that's where we actually do the log, I'm not quite sure. Okay, so if we're trying to do a pointer offset, we've got an example here where we've got a task structure being passed to enqueue task fare. So what we're doing, x1 is the second argument. We've put brackets around it, and we said we would like to offset that at 1520 decimal, and we'd like you to treat that as a string. And that brings us to offset, and we treat it as a string. Bear in mind that the whole string and pointer thing, this is an embedded string built into the structure, which is why we can do that. If we had a char star, we do have to dereference it at offset 0 to get the underlying string from it. Just that kind of syntax. You can line these up. So if you've got double indirection within structures, you can do multiple indirects, so that takes x0, offsets it at 40 decimal, and then offsets it at 0. So that means you can navigate pointers tremendously effectively, but it gets complicated. You have to look this stuff up. There are tools coming up in future weeks that can help us write those probes. We're not going to cover them this week because I'll run out of time, but they do come up. And then finally, before we move on, some trace options. So one of the things that didn't come up is the tracing options directory. So I've glossed over this one until now, but there is an options directory inside tracing, which allows us to manipulate a couple of interesting things about the tracer. So among one of them that's in here is trace TP-printk, trace printk, I think it's called, which allows us to control whether or not trace points are sent to the printk buffer. It's equivalent to the TP-printk option. I can't tell you what all of these do. We have certain interesting ones, things like print parent, sim offset, annotate, control how the functions are textualized when they come out. So I don't often change the options, if I'm honest. I usually find the defaults are essentially right for me. But if there are things that you find distasteful, it's definitely worth having a look at the options to see if they can be made more tasteful for you. Right, I have to somewhat accelerate through this bit now because it is something that should be familiar from previous weeks. So last week we looked at what IRQs off, preempt off, and wake up do. They're basically latency tracers that look for things like maximum periods with interrupts locked, maximum time from a wake up until a task gets executed. We've introduced a wake up deadline, which you didn't see last week, which is for a new scheduling class, the deadline scheduler. So we can only look at latencies affecting deadline tasks as well as just RT tasks. So we really can zoom in on the set of tasks that are likely to be interesting in real-time workloads. It looks somewhat like this. So tracing IRQs off is going to record where the IRQs were off for the longest period. These things aren't trivial to read, as I remember. So this was the latency. Yes, that's the latency observed, maximum latency. This is where it was observed, and this is the stack trace when it was observed. So you can see here the distance between the lock and the unlock. That's measured the time that the latency came from. That's a compensatory delay, which is why I think we get to 48. And then this is the extra costs of gathering the stack trace to tell us what's gone wrong. So that's what we get with the latency tracer, kind of useful. The other tracer I'm going to bring up for you is the branch tracer. The branch tracer is kind of interesting because it's there mostly to study the macro likely and unlikely that appears in various places. So branch predictors are obviously important for performance. And one of the things we can do with the tracing system is instrument likely and unlikely so that when we take a branch, we can figure out where we've got likely or unlikely wrong. So we can profile annotated branches, which is the one that tracks likely and unlikely. We can actually profile all branches, which I think uses a special compiler mode, but I haven't gone into that in great detail. And once you've got the branch tracer available, you can trace likely and unlikely as events in the record buffer. So you can look and see when you've hit it, when you've missed it, how often. This is more useful when attached to a profiling system that can crunch the stats for us, which we can do, but we're not going to cover this week. But it's an extra feature that's in there inside the tracing machinery. So when you look at the branch tracer, it's there to track correctly or incorrectly predicted branches. So we're now coming back to answer one of the questions from the chat about other ways to exfiltrate data. So I mean, the straight answer is, are there alternatives? So the question is, are there alternatives to get the data out beside cat? Yes, because the trace is just a normal C file. So any tool that can read cat and do something with it that is useful is an alternative way to exfiltrate the data. So it all sits on top of the same POSIX machinery, but instead of using cat in the console, we can use other techniques. So trace command is one of those simpler textual CLIs that gives us some extra features to work with the trace buffer. It has features for things like recording past the size of the buffers. So first, trace command is internally structured on the whole subcommand structure that Git made popular. The main subcommands are things like record and report. So record is a mechanism to gather the data and exfiltrate to disk. So it is able to manage the process of sucking on that trace pipe and writing out to disk as fast as it can manage to allow you to have traces that are much bigger than RAM. It is possible to trigger specific things, like we can extract the buffer to only save the trace buffer on particular events. I beg your pardon, when it stops. So extract buffer will basically sit there and record to disk the buffer as something happens. I believe you run it until it exits, and you've used a trigger to no trace something when you've had enough, if you like. There's also support for network transfer. So you can be throwing all the trace information off system and archiving it somewhere else, although obviously that will consume quite a lot of your network bandwidth. So trace command is a really good tool for gathering data and hurling it out to somewhere else. It also helps us a little bit with the configuration. So for example, we have a trace command here that is going to do a record into a trace file of these trace points. So while trace command is running, those trace points will automatically be enabled. And when trace command is Control-C, it will finish writing out the data to the buffer, clean things up, and get rid of the enabled trace points again. So this is no longer the low level approach. This is great if you are working on something like Open Embedded, where you can have trace command. It's a little bit more painful if you're working on an Android system where you have to figure out a way to get trace command on there in the first place. Which is why we start by looking at the lowest level stuff first, because that's common to everybody. There are simpler ways again to set up various types of trace. So -G will give you a graph trace of the scheduler tick function, and I believe only the scheduler tick function. So function graphing, I've showed it being desensitized. It can also be sensitized by particular functions, and that's the final story that we look at before we finish. So in this particular fragment of shell, we've modified the size of the trace buffer. We've looked it back just to see what's happened. We reset the trace system, and then we start running a function graph trace on a particular set of trace functions. And this one's set up so that we don't have to Control-C it. We can start it, which will start it working, and then we can stop it and extract it. So this doesn't record as we go. This will loop round, and the assumption is that something will have stopped it after something interesting has happened. Maybe we trigger this from user space when we spot something's happened. Maybe we've used triggers inside ftrace to cause it to stop automatically. But anyhow, once the trace is gathered and we're finished, we can stop it, extract it, and then we can start working with it. On the right hand side, what we're demonstrating there, we're demonstrating exactly the same thing but using trace points instead of function graph tracing. So again, we're able to sensitize ourselves to a certain set of trace points, and we can extract at the end when something's happened. So trace command has a number of features, not least of which is a wraparound histogram, which has -- help on it, which is never a bad thing to have. So it's a very simple tool, trace command, but it does add quite a lot of comfort on systems where you can run it, and it automatically handles the streaming to different places. I mean, you can trivially use something like Netcat to exfiltrate directly from TracePipe if you're running on a simple Android system and you've got a BusyBox or a toy box with enough features. So you have capacity to exfiltrate over the network using simple Unix pipes, but trace command does wrap it all up in a much more comfortable shape. Going up the value chain of tools, we also have Kernel Shark. So Kernel Shark is the sort of preeminent GUI tool for browsing trace data. It's actually a partner to trace command. It lives in the same Git repository, and it reuses the same file format. So those trace.dat files that you captured here can be directly loaded into Kernel Shark. You have to do a tiny bit of fudging if you have a raw trace file to get Kernel Shark to load it. Kernel Shark shows you a fairly extensive graphic visualization, and it has been tuned relatively recently to cope with very, very large volumes of trace. So the tools to zoom in and out on those graphs are able to run very, very quickly. It's like running a scroll wheel, and it moves in and out. It's very comfortable. And its real great feature, Kernel Shark, is this thread schedule that shows at the top here, which is if you've got the appropriate trace points up so you can observe the context switches, then it colorizes the different workloads. It allows you to hone in on particular patterns, because certainly when you get real-time problems, if you've got a real-time system with a really strong thumping heartbeat, like the VSync on a television, then you can see when it goes wrong, because if you miss a frame boundary, there's this chunk of dead space when it just doesn't look right. You know where to zoom in visually. So the visualization can be quite interesting for studying things. It also has the capacity to go into every trace event, search through things, look for things, find things, match up the graph, view single threads. Normally it's a CPU based view with different colors for different tasks. You can zoom in and draw the graph for specific tasks. So it's got a collection of ways to draw what's happening. And if the problem that you're trying to analyze is one that visualization helps, then Kernel Shark is a terrific tool to do that. And then at the top end, I say top end, if you've got a really complicated tracing scenario, then Lisa is a fantastic system for, I think you'd call it interactive computing these days. The idea is that you're writing Python scripts as you go to study the log. The way I express it is, when you do trace, you will think to yourself, if I just wrote a Perl script or a Python script, if you're a bit more modern, that could walk over this, then I would be able to summarize the information in an interesting way. And so I'll gather that text log, I'll write all the text parsing code, I'll pull out the records, I'll study it. If you are starting to talk about that kind of quick script that walks through a piece of code and gives you some interesting summary, it might be a good time to look at Lisa. Lisa is not a simple tool. It is not, I will be honest, a tool that sits in my toolkit very often. I know about it. I haven't yet had a really good opportunity to use it in anger, partly because I'm a support engineering consultant and we don't get to do the same thing for very long. Lisa is the sort of thing that schedule engineers use because they work all the time on the scheduler. They develop a good toolkit. Somebody who is as generalist as me just doesn't get the chance to use this quite as frequently. If you're interested, Lisa actually grew out of the ARM scheduler team. So when they were working on the second or third generation Big Little schedulers, this is where Lisa came to the front as a tool to help them understand scheduler behavior. So it's an interactive computing environment built on top of IPython that provides you a notebook to work in. So notebook is a concept from many interactive computing tools like Maple, Mathematica, Sage. It's basically chunks of code that you can press return and they execute on an engine and store the results in a file so that you can look at your work back and compare the output between runs and things like that. So it's a difficult concept to explain, but fire up Jupyter and you'll get a sense of what interactive computing means in that sense. The reason it is useful is because what Lisa is, when you take away the fuss, is it's the really powerful interactive computing environment of Jupyter, combined with libraries to make it comfortable to interact with the target, both on Android and on regular Linux. So essentially what they do is they've got a collection of precompiled binaries as part of this devlib that it copies onto the target. And it's then able to use SSH and ADB to manipulate and command the target to do some interesting things. One of which is to set up ftrace and generate trace.dat files. From there, you have this library called Trappy, which is able to parse ftrace information and push it into a NumPy array, the Python numerical processing system, which gives you the capacity to walk over these things quite quickly, and you can do complex studies of the trace data with relatively little code. And then you've got BART, which is an assertion framework, which allows you to go over a trace buffer and confirm that certain assertions about the trace are true or false, i.e. there is always less than 20 milliseconds between event A and event B. Classic assertion that you might want to put into a scheduler analysis system. So Lisa is really powerful. We will have a demo of that power right at the end. But it is a complex tool. It is a real investment to learn. So when you are doing simple debugging, this is not what you'd reach for. When you are doing long-term tuning of a complex piece of code, then Lisa becomes a phenomenal tool. So finally, our last 10 minutes, we will be looking at some debug stories. So the first story is actually just a bit of self-education. we would like to better understand some complex kernel working flow. And this is a really good use for ftrace, even if you haven't got a debug problem in front of you. It's a really good tool for self-education about learning exactly how a particular subsystem works and interacts with its neighbors. It really is rather good for that. So I love pointing this at I2C if I need to remind myself how I2C works. Sorry, that's one of my canned demos, so it's not part of this course, however. But yeah, it's a really, really fun thing to do to learn how these things work. So the reason it's important is, as I said last week, static analyzers are vitally, vitally important. But the kernel is full of function pointers, and it is not that uncommon when you're working with the source nav to find it difficult to statically analyze the execution flow through a function pointer. Sometimes you can do it. It is quite possible with grep and a few other tools to find the corresponding functions, but not always. Occasionally that function call does elude you. So we'll start by using the function graph tracer to help us understand that complicated working flow. And this is using a feature we haven't looked at in any detail before. So over on the right hand side here, you can see that we're interested in the CPU frequency. You'll see it coming over and over again. The guy I co-wrote most of these slides with is a power management engineer. So all the examples he wrote are dragged straight out of power management systems. So he's put a set graph function on CPU freak driver target. And he's then launched a function trace based on it. Now what that does is it means when we execute CPU freak driver target, sensitize the function trace. So we will only trace CPU freak driver target and its children. So what happens when we do that is we see a bazillion RCU calls. Almost whatever you trace, you will see a lot of RCU calls. They just crop up everywhere. You might find they're feeling a little bit in your way. So what we will then do to our trace scenario is we will add in a couple of things to get rid of regmap reads and writes, because in this instance we don't really care about them. They're just ways to interact with registers. We decide to get rid of wait for completion timeout, which is a particularly long and exotic function that, other than knowing it's executed, isn't often that helpful. We get rid of some of the RCU stuff, and now when we run it, we get a much smaller set of code. So this is exactly what we mean about setting up filters. You run a test, you observe the data, you think, oh, I don't want to know about all that stuff, so you get rid of some of the noise. You can, of course, filter it after the fact as well, particularly if you've moved stuff onto a off-device analysis system, but it is quite convenient just to be able to throw away information on the target and keep running and testing. So here we can now see that when you call the CPU freak change, this is a high key 620 as it happens, and you can see that it realizes the clock change by going into mailbox system, sending a message. You get a really clear view of how a high key 620 copes with CPU frequency change. You don't really know what the microprocessor on the other side does, but you do get that clear view that when you want to change CPU frequency, that's what it is. And that's perhaps why you couldn't find the code to change frequency, because it's not actually on this system, it's happening on another machine. What do we want to run the other way? So not only do we want to know what CPU freak driver target is calling, but who called us and why. So let's try and see the other way as well. And we can do that by dropping a stack trace command into set ftrace filter. So what that's got is we've now got the stack trace command attached as a trigger to that particular function. So every time that function runs, we will see the stack trace. And now we have this fantastic visibility in both directions from the function that we're tracing. So every time it's called, the first thing it does is print a call stack of where we were called from. That's already awesome. I mean, even without any of the function graph tracing, just being able to say, give me a call stack whenever you execute that function, that's awesome. So we've got that. And then we will see all the calls that function makes, just as we saw on the last slide. And every time it gets called again, we'll see where it gets called from next time and next time and next time. So it's a really good self-education tool to reinforce any source nav you do, particularly if it's a scenario you can set up. Even if you can't reproduce the bug, you can find out which bits of code are involved and reinforce your source nav. So it's a really cool bit of trickery you can do. The second story is this one where we introduce Lisa to you. and kind of give you that real sense of what it can do in the hands of a skilled user. So before we launch this one, you don't have to remember every detail of this. Basically, I don't want people to walk away from this feeling kind of stunned and believing they'll never manage to use Lisa. It has power. It does take effort to learn it. You should learn about the sort of things it's good for working on. What you should be trying to remember from this part of the presentation is what and when you should deploy Lisa. And that is when you have a complicated problem that you can afford to invest the time in to make the tool work. Quick stuff, no, to be honest. It is difficult stuff, and it is difficult to set up. So this is what Lisa can do in the hands of a skilled user. So we start off by setting up a tracing scenario. So we have a particular problem, which is that the big. LITTLE scheduler is not spinning up correctly and passing tasks over to the big core. So we set up a whole bunch of scheduler trace points that we think will be interesting to help us understand what's happening. So we tell it where the trace file should be, we tell it what events are going to be passed, and we ask to launch an ftrace with those particular sets of events set up. And then that's a cell, incidentally. So you can see this in 5. That means that's a cell in our interactive workbook. We can execute it, and it will remember the output for us. And if we save the workbook, that's what we'll wake up to next time. So the data will always be there ready for us to look at again. So if you were to reload this in the future, trace.that would still be there. You could jump straight to in6, press return, and it would have the same effect as it ever did. This is what interactive computing is all about. It's mixing together the history with the computation so that you can reproduce results and play with them and fiddle. So what we've asked it to do is to plot the ftrace buffer that it just got back, do a task placement graph. So this is similar to what you might see on some kernel shark systems, but that's what it's doing for us. So I'm not usually in this office this late in the evening, and the sun is really streaming at my desk. So I know I'm dark now, you can't see me, but otherwise I can't see my screen properly. Global view for task placement. So this is the task placement graph, and what we're seeing is this big green chunk, which is running on CPU 6, one of the big cores. And it shouldn't have done. It should have been able to transition down onto one of the little cores because there's space to fit it on a little core. And if we can fit something on a little core, we would prefer to do so. So it's odd because it shouldn't take 3 seconds to figure out that the task is not as complicated as we thought it was. So we go in and we go a little bit deeper. So we use a different type of plot. We ask Trappy to draw us a line plot of a specific signal and a particular trace point and one of the arguments of it. So it's basically looking at the utilization average coming out of the one of the scheduler trace points. Then we've got some stuff about how we set it up, the filters and things like that. Like I say, you do have to go and read the manual to find out how to write those lines of code. They are not things that you remember out of the top of your head unless you've been doing this for a very long time. But what it shows us is that the load tracker has correctly figured out in about 1/3 of a second that the cost of this task is relatively low. So that's told us that the load tracker has done the right thing, but for some reason the scheduler has allowed the task to remain on the CPU for a whole extra 3 seconds before transitioning it to a little core. Curious. So this is where domain knowledge comes in, and this is the other reason why it can be why demonstrating things like Lisa is quite difficult, because you have to remember that these codes are written by people who understand the code that they're working on. And when you're debugging your driver, I would hope that you are one of the preeminent experts of the driver because you've written it. So here we are starting to apply a certain amount of domain knowledge. We've looked at the wake up, and we look at the wake up at the point it's one of the wake ups where it hasn't transitioned a task. And we should have expected to see sched boost task in this set of trace points, and we didn't. So obviously, reasoning about stuff that isn't there does require a lot of domain knowledge. But the person who is doing this debugging knows how the scheduler works. they would expect to see a boost check at this point, and it is not there. So they start going and digging around and looking for what might be going on. And so this is where they can go. So a scheduler author who's been there for a few years can go from there pretty much to these lines of code and say something's not right here. So it's recognizing that boost was missing. That was the clue that helped them step forward. And from there, they've come in here and they've looked at the CPU overutilized code. And what happens when a CPU is overutilized in the modern big. LITtle schedulers is they just give up on power-aware scheduling. And if a CPU is overutilized, they drop back to traditional SMP, spray it across the system to maximize bandwidth. And then as soon as the CPU is no longer overutilized, it drops back to the task packing approaches to save power. And the assumption is that that might be wrong. So you graph it, and you see this massive plummet in utilization. Not the utilization average. That's something else. You see this massive plummet drop as to what we read when we were running in this function. At the point the task transitions, we see this massive plummet in that particular signal. And it turns out that there was a bug in the scheduler code, and the reason for all this was because idle CPUs were not having their overutilization cleared. So in other words, a CPU that goes from fully busy to fully idle was incorrectly being considered to be overutilized because the idle time was not being considered when we were studying to find out if the CPU was overutilized. So you add in the check, you run it again, you do the graph, and you can see now the transition to the low of the little core happens within that half second that you would expect. So that is it for Lisa. That's the sort of thing it is good for. It's when you've got analysis. It has a tremendous graphing capability. The capacity to graph actions from trace points is quite complicated and quite sophisticated. It also has these schemes to help you programmatically work through trace points. So even if you don't want to use the graphs, you can work through trace points and make assertions about them, summarize them, print them in a different form, gather statistics. But there is that significant cost to learn how it works. So some further reading. First off, there is the kernel documentation for anything related to ftrace, events, kprobe trace, any of the stuff we've done by hand today. That's the place to go and look. There are also some excellent LWN articles from Stephen Rosett, who was the primary originator of ftrace. So there's loads of stuff there that you can look at. Like I say, this section here is particularly good, but we also get to see some other LWN articles about trace command and how to use it, kernel shark and how to use it. These are all getting quite old, but I believe they're all still fairly relevant. Oh, that's our presentation thing here. So there are some other presentations that we've had going on at various events. So the ARM guys have been there talking about Lisa. They're really good for explaining how Lisa works and what it's good for. And I think Leo and I made a modest contribution to the presentation space as well. Although again, that's going back quite a long time now, 2016. Reminders, as ever, all Linaro training comes with this lifetime warranty. That means that anybody who has received our training can come back and say, I don't understand what you were saying about the stepping process on slide 7. So yeah, I do encourage people who are asking about training to give me a slide number. You know, for members, it's slightly different. In general, anybody who gets our training, whether through developer services or via members, can use support at linaro.org. Obviously, members can use support at linaro.org for much more than asking about training. We're there to support any question you have about Linaro. But yes, particularly with respect to the courses, the lifetime warranty means if you can give me a slide number, you can ask me a question about it at any point you wish, and I will do my best to explain what that means, what that point was trying to illustrate. Which moves us on to the very last thing for this week, which is the lab sessions. So the lab sessions, I really encourage people to look at the lab sessions for ftrace, because ftrace is that terrific tool that is always available to you, providing you can compile it to the kernel using normal Unix tools, or the higher value ones we've looked at. So it's a terrific tool for studying how the kernel works. I have to say I used it this week to start studying how a particular board was behaving when we were trying to trace something. So I was using the trace system to debug a different part of the trace system, which doesn't usually work, but in this case it did. So yeah, I really do encourage people to look at the labs for this week. The instructions can mostly be carried out on your own machine. So these are documented to run on QEMU, and if you only have QEMU available to you, the tool set is in last week's slides. It was Lab 0, so you should have all that set up. And then once you've got that set up, you can then run this from this week's slides with your own kernel compiled to allow you to fiddle with it. If you are running on a piece of real hardware, almost all the labs should still work, providing you have a I2C peripheral, because most of the labs are there to do with studying the I2C bus. If you haven't got an I2C peripheral, perhaps look at RegMap or other areas, so you might have to adapt, but these can be run on real hardware, providing you do have similar peripherals. If not, like I say, running on QEMU is terrifically good. In this case, you will cover all the material easily on QEMU because it's all software features. Using QEMU works well. Just remember the setup information is in last week's lab. So Lab 0 from last week tells you how to set up this particular open embedded software development kit. This week assumes you've already set it up. If everybody's got the links to the Google document, I will actually copy in that information. So if you look at it tomorrow, you'll actually get a lab -1 that tells you how to set this stuff up. And that is the end of this week's material. So I'm only a tiny bit over, which is excellent. I will give the 10-second pause at the end for anybody who wants to ask any final questions before we close. But other than that, thank you very much for coming. And next week, we should be talking about using the virtual machine built into the kernel, the BPF virtual machine, for debugging purposes. BPF has many purposes, but we will look at how we can apply BPF for debugging activity. So yeah, thank you all very much for coming. If there are any questions, then just throw them in. And if you're on YouTube, then Christine will copy them in. If you're on Zoom, I will see them straight away. Well, thank you all very much indeed, and we shall see you next week.